In the spring of 2022, a lecture was given via Zoom to the audiences of two organizations, the Irish Climate Science Forum in Dublin and CLINTEL, the Climate Intelligence Network headquartered in the Netherlands. The lecture reviewed the Earth's paleoclimatic record and demonstrated how current climate models are ignoring this evidence. The lecture was very well received by the worldwide audience, and this YouTube video includes all of the information provided and incorporates higher resolution graphics to improve the usability. The lecturer is Thomas P. Gallagher, who is an Earth scientist with a wide range of experience in the field.
Thank you for the introduction and for the opportunity to speak to you today about paleoclimatology, the study of climate lessons and real information about ages long ago. In days gone by, Canada and Northern Europe have repeatedly been completely covered by very thick and extensive ice sheets. What do we do to deserve this sort of treatment? Let's set the scene. This talk is going to introduce a lot of material. Note that our emphasis here will be on the data from the Earth science record. More detailed information is contained in 3 videos and links that we will provide on the last slide of this talk. We'll be talking about climate change, not weather. We are talking about long-term variations over large areas. The Earth's climate is driven by the sun. We will review how cyclic Milankovitch variations in orbital parameters affect the incoming solar radiation energy to the Earth. We will examine how energy is stored and accumulated. This is one very fundamental ingredient, which is sadly missing from all our other climate studies that are being done today. The IPCC style is not to look back very far. The movement of stored energy around the Earth by the ocean currents is essential, both in the past and today. We will learn how these transporters and accumulators of energy have changed over time as a direct result of continental drift. This component is also very sadly missing from existing climate models and studies. This is a very important characteristic to trace back in time. We will not look at only the past 200 years. We will extend our knowledge and our database back to times before the dinosaurs became extinct 67 million years ago. We didn't have any scientists taking measurements thousands of years ago, so we will have to use fossil proxies. These fossil proxies, like isotopes, provide compelling evidence that is much more reliable than unproven theories. This presentation will review ancient fossil data from experiments that the Earth has conducted on itself in many times in the past. This data is our Earth climate memory, encased in the layers of rock and ice history. By examining the past, we can learn more about the present, and we can equip and be better equipped to forecast the future. This chart plots historical temperature on the Earth using a proxy. Note that the historical time axis on the horizontal side is compressed and has several time scale changes in it. The present day is on the right side. 500 million years ago is on the left side. 18 degrees Celsius change in temperature is illustrated on the vertical axis. Also note the green Eocene arrow as a reference point at 50 to 60 million years ago, just after the dinosaurs went extinct. There has been significant temperature reduction since the Eocene. The temperature is developed from oxygen isotopic ratios in fossils, sediments, and ice. Over the past 50 million years, the temperature of the world has plunged, leaving the world in a glacial period today, the black Pleistocene arrow P. The last 11,000 years, not very long, are known as the Holocene, during which the Earth's temperature has been relatively steady. We are living during a rare time, this Holocene period, on a small island of warming during a period of extreme pulsating glaciation. Here's an even further look back in time to a period just before the Earth's formation. Using proxies, both the temperature, the blue line, and the atmospheric carbon dioxide, the purple line, can be seen on the plot. Note the strong lack of correlation through time between temperature and CO2. This history is inconsistent with current global warming and climate theory. We will focus on this discrepancy very soon, using solid long-term data, not theory. The Eocene is again shown with the green arrow. Perhaps there is some relationship between temperature and CO2 after the Eocene, but is this really the case? Please note that high CO2 coupled to lower temperature are the rule and not the exception during the formation of the Earth. A severe temperature decline and glaciation is our current default climate of the Earth. The arrows show 3 periods of Earth history, the K Cretaceous, E Eocene, and P Pleistocene for reference later on. How was sea level varying through this same period of time? 3 major glacial periods before our current Pleistocene P, the black arrow, have existed. Lower sea levels generally correspond to these glaciations. Extreme sea level variations do occur, and this chart shows well over 200 meters of such range of sea levels. We will look at sea level again later in the talk. Notably, the rate of change of current sea levels is much more gradual than anything shown here in the past. Let's focus on the period of time that spans between the death of the dinosaurs, about 65 million years ago, and today. The graph, the green line, shows a total temperature fall of between 18 degrees Celsius during this period and now. This temperature fall is documented using fossil shells and ice core isotopic oxygen ratios. Note again some critical time periods with arrows: K, E, O, M, and P. We will address the relationship of temperature to polar ice intervals shown here as a little bit later in the talk. There are some factors which we need to integrate later. The important take-home, however, from this graph is the dramatic global temperature decline that the world is caught up in. This graph shows the same time period, 65 million years. This slide has been modified from a green line to a colored line, red for warmer and blue for colder. There's a very distinct break at the O in the middle. Please note that. Please note the heavy blue line at the top right side of the graphic box. This blue line represents the polar southern glaciations of the globe, coincident with dropping temperatures over time. South polar eastern Antarctic glaciation began 34 million years ago at an abrupt change in temperature shown by the yellow arrow, O. A minor warming followed this and culminated near the M Miocene blue arrow 14 million years ago. After this, a rapid and enduring fall in temperature led to the formation of the western Antarctic ice sheets. There was still no Greenland ice sheet or northern ice cap until much further and much later on, the black arrow P. Northern glacial ice finally formed at this time, coincident with a strong fall in global temperatures. We are living at a time on the right lower corner of this chart, 16 to 18 degrees below the green Eocene peaks. What has caused this dramatic temperature decline and glaciation? The answer to this question comes from looking at the largest fundamental factors in Earth climate and their changes through this long history. Solar, ocean energy storage, accumulation, and currents, all modified by continental drift positions. Solar, the sun. There is no other significant source of energy to drive the climate system of the Earth. The oceans. provided the long-term accumulation of storage of that solar energy. This is a fantastic energy absorber and is a cumulative circulating collector of solar energy over long periods of time. The ocean currents. The energy is collected and transported around the Earth by the ocean currents. These currents of energy have varied over time and have a unique history, which we will very shortly track. In stark contrast, the atmosphere is not a place for long-term climatic energy storage. The atmosphere, notably there, the water systems again dominate and dump some of their energy back to the ocean, and the rest is radiated to space. Oceans represent 71% of the Earth's surface. Oceans have a very low albedo, which means that they are excellent absorbers of the sun's energy. The best of all of the Earth's surfaces, oceans absorb more than other albedo sources or other natural surfaces of the Earth. In our climate system, only water can exist in all three phases at our normal temperatures of Earth and pressures of Earth. As water changes between phases, energy is absorbed or released as latent heat. Water retains an anomalously high specific heat. Unlike water, carbon dioxide exists only as a gas in our climate system. It does not undergo phase changes, as is a very poor and very short-term retainer of any energy in the atmosphere. Water absorbs or releases latent heat as it undergoes phase changes. This is why water storage and accumulation dominates the climatic cycles of the Earth. The currents of the ocean are the largest energy transport system on the Earth. As the continents have drifted due to tectonic plate motion, oceanic passages between continents have opened or closed. This continental plate motion has resulted in significant changes in the Earth's network of ocean currents. These changes to the energy distribution system have created major historic climatic variations. Some changes have promoted climatic optima, while others have resulted in cold glacial times. Over 200 million years ago, the Earth had a single supercontinent called Pangaea. About 175 million years ago, Pangaea began to break up. As the underlying tectonic plates shifted and split. As these pieces drifted away from each other, they began to gradually form the continental shape that we're experiencing today and we recognize today. We will trace this movement from about 66 million years ago. The K, Cretaceous, late Cretaceous pictured here, just before the dinosaurs went extinct. It was a completely open equatorial seaway that allowed the oceanic currents to circulate freely around the warmest part of the Earth, accumulating and distributing solar energy and influencing climate. Temperatures were high. Water levels were high. No ice caps existed. Life was abundant. In the Eocene, E, following the death of those dinosaurs, this equatorial seaway remained open and was stronger. Strong, warm ocean currents existed and allowed cumulative oceanic solar energy to accumulate and be stored. Note that India is moving northward. In the southern hemisphere, the Drake Passage was closed. The Tasman Strait between Australia and Antarctica was closed. Australia and South America were firmly joined to Antarctica. At the North Pole, the Arctic was closed and contained a large freshwater lake. There were no polar ice caps on either pole. Cumulative energy collection, storage, and warming of these equatorial currents occurred, and the Earth climate was at an optimum. Global temperatures between 16 and 18 degrees Celsius above today existed. Biological blooms due to upwelling ocean currents occurred. This was an uninterrupted El Nino on steroids. with open equatorial warm waters circulating, collecting energy and heat over time. This condition was long-term climate altering, warming, and positive for biological growth. In the Oligocene, O, the yellow arrow, about 34 million years ago, major plate movements, collisions, and changes occurred. Temperatures remained warm until the seaway openings occurring at both poles happened, and some major closings of equatorial seaways happened as well. India, if you know, was colliding with Asia and partly closing the Tethys Seaway, the Great Equatorial Seaway. The Arctic opened, and the Drake and Tasman passages also opened, allowing cold circumpolar currents to dominate and isolate the southern pole from the rest of the world. The southern, eastern, and Arctic ice sheets began just now to form. In the mid-Miocene, M, 14 million years ago, the Panama Passage narrowed between the Atlantic and the Pacific. And the Indonesian-Australian area narrowed, changing the connection between the Indian and the Pacific Oceans. The conveyor of warm equatorial water and collector of energy in those waters was shutting down. As a result, southern polar ice caps expanded into western Antarctica. The isolation of Antarctica by circumpolar currents became stronger as the southern polar ocean widened. No northern polar ice caps have yet formed. Finally, 3.3 million years ago, Panama and Indonesia closed to terminate the equatorial ocean current, the conveyor and accumulator of all that energy. The world's currents are forced now into a whole new configuration, north-south. Northern and southern ice caps expand with the addition of sea ice sheets during peak glaciations. Large 41,000 and 100,000 year-long glacial cycles begin. Drastic 10-degree centigrade cooling swings, punctuated by the solar Earth-Sun dance of the Milankovitch cycles, are now evident. The world spends most of its time as glacial, cold, dry, and very dusty. The closure of the Isthmus of Panama is documented by fossil changes and chemistry changes between the Atlantic and the Pacific Oceans. The migration of animals across the land bridge formed also documents this closing. A large gap that once existed and allowed the equatorial currents to flow was rerouted from east-west to north-south. A similar closing occurred between Australia and Indonesia at this time and terminated another significant part of the former equatorial currents. The global climate abruptly changed and cooled. This is what it looked like in temperature. This is the temperature of the last 5 million years. Panama and the P, Pleistocene arrow, the black arrow, are shown here. And they send, at that point when Panama closes, they send the Earth into the Pleistocene ice ages, further reducing oceanic energy storage. Strong glacial and interglacial periods bounce up and down in overall declining temperature system, the blue jagged line. Solar cycles of the Earth-Sun system become very evident in the 41,000 year and 100,000 year cycles shown by the peaks and then the green portions of those peaks. Global temperatures continue to fall. We have arrived at the Pleistocene, a time of extreme adaptation and change, a time that we now somehow feel is normal. The information presented so far has been derived from a variety of different proxy data, as we mentioned, isotopes shown here. Understanding continental drift has enabled us to analyze the most significant factors at work and compile them into a real geologic time-scaled story. In 2020, then, a new source of excellent proxy data became available, This covers the past 67 million years with a high sample density and accuracy. It is based on isotopic analysis of microscopic, fossil, benthic forams. These fossils have been recovered from deep sea cores from multiple drill sites all around the world. This compilation by 20 authors under Westerhold of Germany depicts the full 67 million years in great detail. The data is known as the CENOGRID. The shells of those microscopic fossils were sampled. The analysis was conducted on their carbon and oxygen isotopic ratios to arrive at some startling conclusions. The ratio of oxygen 18 to 16 isotope is affected by the temperature, and the ratio of carbon 13 to 12 isotopes is indicative of the CO2 concentration. Here's the plot of the oxygen 18 to 16. This ratio is our proxy of temperature. The error bands are indicated in the blue, and the best fit data is plotted in the red. The total equivalent temperature range between top and bottom is 18 degrees centigrade. For reference, the E, O, M, and P times are shown. And they were referred to, of course, earlier, and they relate this back to continental drift maps that we showed you. Here we have also added the plot of carbon 13 to carbon 12. The isotopic ratio there is indicative of the carbon dioxide concentration at the time. Alarm bells should be going off because we note that the CO2 and the temperature do not correspond or move together consistently in this data. Perhaps there's some other controlling factor that needs to be considered. Major volcanic events are shown as orange triangles. Significantly large injections of CO2 by volcanic activity into the atmosphere do not have the predicted temperature effect that current theories might suggest. To try to analyze what is going on, Westerhold et al. Used a modern tool known as recurrence analysis and applied it to their data. These recurrence plots allow our eyes to see the pattern of temperature on the right versus CO2 concentration on the left graph. The pattern of the plots definitely shows a lack of symmetry. However, popular theory would say that the two plots should correspond and mimic each other. They do not. We conclude that temperature and CO2 are independent variables that do not covary. The data sets do not, however, have everything not in common. They have some small black arrows of times, as you see on them. They are all coincident with major continental drift events in geologic time. In the 1920s, Milankovitch theorized that cyclic variations of the orbital parameters of the Earth as it moves around the sun would affect the magnitude of solar radiation that strikes the Earth and creates climate variation. These are the three Milankovitch cycles with periodicities of 24, 41, and 100,000 years. These Milankovitch cycles are due to cyclic variations in the eccentricity, that would be the distance, the axial tilt or obliquity of the Earth, and the precession or wobble of the Earth's axis. These cycles combine, either constructively or destructively, to alter the resulting solar radiation that is striking the Earth's surface. Westerhold et al. Saw a pattern in their data and began to investigate it using Fourier analysis, a technique performed on time-varying data to look for repeated cyclic patterns in the frequency domain. Their FFT analysis of the fossil isotopic ratio data yielded spectrograms of repeated cycles, and in them was buried in the data a frequency that was the Milankovitch cycle. Their FFT analysis of the fossil isotopic ratio data yielded a spectrogram of repeated cycles buried in that data. Their frequency analysis independently produced the Milankovitch cycles of the Earth-Sun system. They found 405 and 100,000 year frequency cycles They also found 41,000 and 24,000 year cycles. Near modern glacial times, the 100,000 year pulse, the eccentricity, begins to dominate. This analysis sees the heartbeat of the solar Earth Milankovitch cycles, the real foundational energy driver of the Earth climate system. Shortly after Westerhold et al. Published their paper, Essenbach took the same CENOGRID data and replotted it in a format that is much more usable for studying the Earth's past climate. He plotted the temperature on the vertical axis and carbon dioxide concentration on the horizontal axis. Hotter reds are up, colder blues are down. CO2 ppm is plotted on the horizontal axis, increasing logarithmically to the right, between 180 ppm on the left and 2000 ppm on the right. The data covers time from 67 million years ago to about the latest glacial maximum, LGM. The colored continuous line drawn through the data points is the trace of time moving through the chart from 67 million years ago to the LGM. Our contribution to this plot will be to show the message of the continental drift that we referred to earlier. As we now see, there are large steps in temperature between openings and closings of the ocean current seaways. E, O, M, and P represent the geologic ages from our continental drift maps corresponding to the long, uniform times between continental movements and significant openings and closings. This follows the colored line through time. Let's do it. The first step of temperature started 67 million years ago in the late Cretaceous and is circled in the figure. During this period, the CO2 concentration varied by a factor of more than 2 times, with only minor variations in temperature, a rather flat profile or temperature step. This was then followed by the Eocene, a time of open equatorial seaways and thermal collection that dominated the warm Earth. The temperature remained very constant despite CO2 concentration varying and more than tripling. This does not fit greenhouse gas theory. The Eocene is another step of relatively constant temperature, irrespective of CO2 moving between 600 ppm and 2000 ppm. Temperatures did not move. This was then followed between 47 and 34 million years ago when CO2 concentration was relatively high and steady, but the temperature dropped by almost 5 degrees. CO2 and temperature do not match theory. However, the whole heat engine is beginning to shut down, and the Southern Ocean current system is opening up. Then came the Oligocene, O, the light blue line segment, a very long, even temperature step where the CO2 concentration varied by almost 3 times, with no corresponding increase in temperature. This CO2 temperature mismatch suggests even more greenhouse gas theory problems. Glacial ice caps continued to form on eastern Antarctica as it became isolated from the equator by polar currents. The Tasman and Drake passages have begun to open. Then another temperature drop of about 4 degrees in the mid-Miocene, even though the CO2 concentration was fairly constant. Temperature and CO2 again moved in opposite directions to greenhouse gas theory in this period of over 10 million years. The drifting continents then shifted again, culminating in an ice house of the Pleistocene P, where CO2 concentration dropped by 35% and the temperature dropped by 4 degrees after Panama and Indonesia, Australia closed. The continents had moved to block equatorial heat accumulation and plunge the Earth into repeated glaciations driven by Milankovitch Earth-Sun cycles. Ice caps flourished at both North and South poles during glaciations. At the present time, we are still in that ice house. We will look at our current interglacial warm period, the Holocene, soon for a greater understanding of this unique time. So in summary, There are distinct steps of constant temperature that correspond to times between major openings and closings of ocean current seaways. CO2 and temperature do not correlate through this long time series data. Each temperature step can be represented by any ppm number, high or low, in the readings of CO2 concentration. Climate, CO2 theory, and IPCC work cannot, therefore, accurately guess what the temperature related to a specific CO2 reading might be. They have drawn a straight line through time between convenient end members without any attention to the changing dynamics of the geology. Let's look at a recent glacial ice history. This will help us to understand the conditions after Panama and Indo-Australia closed and narrowed. In this ice core data, we see the most recent 100,000-year Milankovitch cycles of glaciation and spikes. There are spikes between them of warmth, but long, lengthy zones of glaciation. The LGM is marked. The proxy of temperature is shown in blue, controlled by Milankovitch. The CO2 concentration is in green. CO2 from ocean heating and cooling follows that temperature data. A seldom mentioned dust curve is shown in red. Dust came from the deserts of the cold, dry world that was left bare of vegetation during the depth of the glaciations. Worldwide dust storms were prevalent during glacial maxima. How much solar power does it take to extract the world from a full-on ice age? Cumulative Milankovitch solar energy cycles are shown in blue above. For reference, the 100 watts per meter squared arrow on the left side is the solar radiation difference between summer and winter in the Northern Hemisphere. Milankovitch cycles show about the same variation in the incident radiation on the Earth, 100 watts per meter squared. Notice how the blue solar cycles attempt on multiple tries to extract the world from the last glacial maximum, LGM. They only succeed when all cycles combine constructively together with the ice albedo changes due to dust accumulation. This escape from an ice age is called a termination. On average, terminations took only 6,000 years to melt out at the end of the last 9 major glaciations, as shown here. Solar power, timing, and dust albedo changes appear to have combined to raise the temperature of the world by 10 degrees or more and melting the world's ice caps and sea ice to leave us today in warmer periods like the Holocene. Over the past 20,000 years, since the last glacial maximum, the sea level has been rising at 40 to 60 millimeters a year, but it has slowed to 1/20th of that rate over the past few thousand years of the Holocene. We will now focus on that Holocene, which is the short-lived warm period that we now experience. It is a brief rest from an extreme cold Pleistocene glacial period. This graph shows the last 11,000 years of Earth's temperature in black. The atmosphere, the CO2 concentration is in red. In this pre-industrial time, please note that CO2 is rising during the cooling period of the Holocene. Unusual. The temperature is following the purple arc of the obliquity or the tilt of the Earth's axis, not the CO2 in any way. Note that the hottest times show the lowest CO2 values, the inverse of greenhouse gas theory. The Holocene can be divided into 2 parts. The early higher temperature optimum part, the thermal maximum of the top map, and the neoglacial half that we are living in now, the lower map. Humid and wet areas in the upper map have been replaced by dry, desert-like neoglacial conditions now. we are now living in the Neoglacial. The latter Holocene is the time of man's civilization and civilized history. The green vertical stripes are shown on the right side of this illustration and labeled Minoan, Roman, medieval periods, etc. Please note that the temperature fell over the Holocene timeframe, and the Little Ice Age blue is recorded worldwide in ice fields, alpine ice fields. CO2 and temperature moved in opposite directions. CO2 rose as temperatures fell. What about the rates of warming during the Holocene? Note the sharp jumps of temperature of 1.5 to 3 degrees Celsius that exist from this fairly recent time period. These were times long before any modification to our atmosphere. Note how abruptly the black lines, up arrows, warming, change from that warming trend to the purple cooling trends, down arrows. By taking the slopes of the warming from the previous ice core graphic and converting them into numbers, we get the rate of change of the Holocene's warming temperatures in degrees C per year, as shown in this plot. The current warming period is on the extreme right-hand side of the graphs. Older warm periods are on the left. The older optimum Holocene showed much faster rates of warming than the Neoglacial times now. The last 11,000 years has seen times of much stronger rates of warming than we are currently experiencing. Now, briefly turning to the last few hundred years, I would like to discuss a few of the things that are similar from the past and contribute today. The primary influences of climate and weather are still with us: solar cycles, oceanographic currents, oceanic oscillations, regional oceanic energy conditions that all drive long-term climate variations. Recent solar activity does correlate to recent temperature and climate history. As seen here, solar activity was low and corresponded with the cold Little Ice Age. Solar activity has increased into the modern thermal maximum as shown. Cosmic particle bombardment of oxygen and nitrogen in the upper atmosphere generates an isotope beryllium-10. This interesting proxy inversely reflects the increase in solar signal over the past 600 years. Note how the solar signal is stronger and is climbing based on this proxy. Today, these well-known ocean currents are the major oscillating energy collectors and storage drivers of our modern climate variation on a regional scale. This global image of oceanic currents, warm red and blue cold, show the truncation and redirection of the equatorial currents as they are deflected and they become spin-offs into the Gulf Stream and the Japanese current. The strong Antarctic southern polar currents are still with us and isolate Antarctica from the global variations of the north. One of the most influential of the current systems is El Nino Southern Oscillation, ENSO, because it has a large, uninterrupted Pacific equatorial span to collect energy. It is going to be able to accumulate significant solar heating. Of course, El Nino and La Nina alternate and control the rainfall and temperature regimes through a significant part of the Pacific world. Wet becomes dry and then changes back again as the climate alternates in this, our largest remaining equatorial heat and climate engine. These current systems are what modify our weather and climate variations along the Pacific. Rapid change is evident. These oscillations that drive regional climate are important. The period from 1870 to 2014 is shown here in a spiking pattern of warm to the red and blue to the cold. 10 or more years elapse between these spikes of hot, cold, wet, or dry. This is the Arctic polar vortex in purple of deep winter cold temperatures that cover North America. This cold, high-pressure system is kept in check by the surrounding moderating oceanic influences. Seems very evident in this particular illustration. And then there is the Atlantic Oscillation, which is driven by cold, dense waters from the pole and the warm Gulf Stream waters from the south. This pulsation is looking fairly predictable now. Here's a look at the period 1856 to 2013, which had a very regular pattern of heating and cooling. This is NASA's imagery of the warming influence of the Gulf Stream waters, which makes Northern Europe so habitable today. This, of course, is in stark contrast to the very first slide of our deck today, which showed the massive ice sheets only 20,000 years ago that covered much of the Northern Hemisphere. Which would we prefer? Which would you prefer? The latest glacial maximum or the Gulf Stream spa? So, what have we discovered from this brief glimpse at paleoclimatology? Firstly, climate change science is badly needed and needs to be involved in all the facts from it and information from the earth sciences that are available. Theory must be consistent with millions of years of evidence from real data. It is not. Earth temperature is not controlled by or directly related to CO2 concentrations over 200 parts per million. Oceanic energy accumulation, storage, and movement have created unique climates throughout Earth's history. These climates required specific continental positions. Only by duplicating these conditions and positions could we ever hope to recreate any similar temperatures. Humans have been lucky to live in the Holocene, a small island of warmth in a time dominated by glaciation. In the Holocene, there is nothing unusual about our current rate of warming. Embrace the warmer, humid, CO2 fertilized times now, but the caution is prepare for more glaciation ahead. Maybe we should be looking to try to anticipate something different. Man's activities are not causing a climate emergency, but we do need to adapt to naturally occurring climate changes, which are more abundant now than they ever used to be. Enjoy the warmth while we have it. And here are those links to a series of 3 YouTube videos provided that you might be able to enjoy and get further detail on certain related subjects. But warning, they are a little bit long-winded. Thank you. Thanks for listening. Have a nice day.
Clickable links for the other reference materials are contained below.